Right. Hello and welcome back to Calculus 3. We are continuing our chapter 17 with line integrals. You have been integrating for 2 years now. And then you reached the multiple integration, and last night, if you remember anything off of that section with the change of variables, I see most of you are back, which means that, yeah, good for you. Now we are going to switch the integration into what we call a line integral. Previous integrals calculated areas, calculated volume, calculated length of the curve. Line integral also calculates the volume. But please pay attention which line integrals calculate area. Sorry, line integrals calculate area. Please pay attention to what they actually calculate. So let's say we have our three-dimensional XYZ coordinate system, and you have some curve C that lives in XY plane. On top of this curve C, I'm going to put like a shower curtain, okay? So this line is going to get a curtain going up like that. All right? And it's going to have some top. This is the top that goes and hooks up to that bar. So you have a curve C on the bottom, and that curve C is wavy, could be circle, could be whatever you want it to be. And then you have the top, and the top over here is going to be some function f of xy. Line integral calculates the area of the curtain. So you are going to have a curtain of some kind, and the line integral is going to compute that. So we can calculate the area of this surface, and this surface is no longer flat, right? Please understand that all areas you calculated so far were flat. They had area as a triangle, area of the square, area of the circle, area between two curves, area under e to the x, but all of those areas were flat all the time, no matter what kind of edges outline it had. So all of the different integrals we learned so far were calculating flat areas on flat areas with whatever edges you had, and different integrals would work with different rules, right? But now you are calculating area of something that it's not flat anymore, and that's obviously what the advantage of this thing is. So I really want you to think of the shower curtain or the curtain on a window or whatever, and understand that it bends around, and the bottom of the curtain, whatever function it draws on the floor, that's this curve C, because you will be integrating on top of C. So what is the scalar line integral in R2? So 2D. Guys, it has to be line integral, and it's line because the curve C. All right, so let's go. Let f be continuous on a region containing a smooth curve C which is given by the parametrization, which is vector r, f of t, g of t, for a less than t less than b, then, and this is the notation, integral over the curve c or f of ds, which is the arc length parametrization, is going to be given by integral a to b f of x of t y of t times the r prime of t dt. This piece is, I hope you remember. I hope you remember this. These are not 12s. This is prime squared. Okay, let me write it as dx. All right. It looks like so dx dt squared plus dy dt. There we go. Oh, that's better. Now the book gives you 1, 2, 3 procedure. Number 1, do the parametrization. Number 2, calculate the r prime, the square root. And then number 3, plug everything in and calculate. So I can write it here in orange. Procedure. Number 1, parametricize C, which will give you R of x of t, y of t. So R is not given to you always explicitly, right? You have to suffer sometimes to find it. That's why I said you need to know how to parametricize. Then number 2, compute absolute R prime. Number 3, plug into integral of f ds and compute. Number 4, win. There we go, done. So that's the procedure. So let's take a look at vanilla problem, and then let's take a look at the applied problem. C is a unit circle. Oh, we didn't cover this yet. Hold on. Brr. Well, let's just make it up. So it's not 10, it's just an example. C is a unit circle. Integrate integral C xy squared ds, whatever. Ready? So, step number 1, parametricize C. So what are the parametric equations that explain C? It's a unit circle.
X cosine or x cosine t, y sine t.
So this is the way you learned, right? The radius goes in front. Radius is 1 because it's unit circle. So it's r times cosine t. R is 1, so just cosine t. Y equal r sine t, so 1 sine t. This is not the way we want to write it, right? We want to write it as the function r of t, which is a vector, cosine t comma sine t. Now these two, this is your x of t, this is your y of t. Part 2 of this calculation is to calculate r prime magnitude. Well, r prime is going to be negative sine t cosine t, and the magnitude of r prime is going to be square root of negative sine t squared plus cosine t squared, which is all 1. Right, the negative will die from a square. You have sine squared plus cosine squared, that's 1. Square root of 1 is 1. So we completed that, and now it's time for us to compute the integral.
You need the limits first.
Oh, the limits are 0 to 2 pi. Thank you. Usually I don't mention limits until I hit the integral, because then I have to use them. I go back. It's a full circle, right? They want a full unit circle, not a half. So we're going to use 0 to 2 pi for the full circle. But if they tell you, I just want a third quadrant, well, it's pi to 3 pi over 2, right? So now, number 3, we do the integral. So integral of x, what did I say? xy squared ds is going to be integral from a to b, 0 to 2 pi. And then we are going to have, instead of x, I have to have my cosine. So it's a cosine t. This one over here is x. And then I need to have sine squared t, and that's my y squared. And then I have to multiply this by 1, which is magnitude of r prime. And then finally at the end I have dt. So you plug everything in. You compute it. You found your r, so you know what your x and y are. And then you differentiate that and find the magnitude to come up with the, what is the 1 in this example. And then after that you just put all of this together, and there you go. Why did I say a? It's 0 to 2 pi. I just wrote 15 formulas in Calc 1. They were all a to b, a to b. I did fundamental theorem of calculus and stuff. So all of my integrals were a to b for 2 hours straight. So I might mess up a few more of these zeros. And here we go. You know you have a terrible instructor when the instructor just tells use u sub and we move on. So use U sub, and then I put a just do it symbol, and then I move to the next example because I don't care about you, obviously.
Zero, right? Isn't it? Oh, never you didn't do the other one.
Yeah. All right. The cool example over here. Figure out the average temperature on the edge of the unit disk. Hey, our C is again unit circle, so it's lame again. Where the temperature function T of xy, so the temperature function is given as 100 times x squared plus 2y squared. So what you have now is a temperature function. You want to calculate the average temperature along the edge of this disk, and you're just going to run the line integral for this one. Now we already know that our C is R parametricized as cosine t sine t, and we already calculated that our R magnitude is equal to 1. We did that in the last problem, so we don't have to run through all the calculations again. So now our integral, line integral, is going to be given by integral, now the circle again, so 0 to 2 pi, it goes around the circle, and we have 100. Now I have cosine squared t plus 2 sine squared t times 1. I didn't write times 1. I should have written times 1 because you are learning. You have to have your R, magnitude of R prime in there. And that's it. So now you know what, let's compute something in life. So kick the 100 outside of the integral, and oh, I picked this problem to integrate, great. How do we integrate squares? Hello, Calc2? How do I integrate this? Each one of these problems is squared. How do I integrate cosine squared? There's no sine for U sub. I'm sorry? Yes, use the trig identity, the power reducing formula from Calc2. There's no other way to differentiate this, integrate this. So we have to use the formula. So the first one is 1 plus cosine 2t over 2 plus 2 times 1 minus cosine 2t over 2, all that dt. So what I'm going to do is I'm not going to cancel the 2. I'm going to kick these 2's outside and make that a 50. And I still have integral 0 to 2 pi. And now what's left in here is 1 plus cosine 2t plus 2 times plus 2, and then minus 2 cosine 2t, and then I have a dt. Which is 50 integral 0 to 2 pi of 3 minus cosine 2t dt, 50 3t minus sine 2t over 2 from 0 to 2 pi. And then when I plug in 2 pi, that's 300 pi. So 300 pi, whatever the temperature units. were used in this, Celsius or Kelvin. Anytime you have a temperature, just send it to people in Kelvin. It's it's the best. I had the flu last semester. Sent to HR, only Kelvin. Go figure it out. Line integral in R3, same thing, just add these. Line integral of FDS is integral a to b of the function given in terms of x of t, y of t, z of t times r prime magnitude dt. So now it's just more annoying to compute everything, right? But still possible. This is a t. And your r over here is the square root of dx dt squared plus dy dt squared plus dz dt squared. So those are, that will be the calculation for r prime. Is anyone seeing the velocity vector there, the speed? If vector r is the path, then r prime is the velocity, and the absolute value of velocity is speed. So that's what that is. It's speed right there. You can replace it with v if you want to. I think they actually will replace it eventually in the book. I know you love parameterization, so let me go and find one of the XYZ parameterizations, huh? The line segment 1, 2, 3 to 5, 4, 0. So we're just going to practice that one as a very important skill. The rest is just plug and chug. Parameter z. It's like Czech language over there. And then we have 1, 2, 3 to 5, 4, 0. This is actually your problem 5. They're just asking you to parametricize. This is the first step. Once you have your r, you can get r prime. You can calculate the integral, no issues. It's just the parametrization could be tricky. So this is a line, guys. You have 2 points in space, and this is the line. How am I going to find the line? I have 2 points in space, and I shoot the line through those 2 points in space. Let's say this is your 1, 2, 3, and let's say this is your 5, 4, 0. And because it's a line segment, we kill these two because it's just from the point to the point. And that's why we are going to actually have the limits a and b, right? Because the t will start here and the t will end there. But we'll cross that bridge when we get there. How do I get the equation of the line? That was your first exam.
Vectors.
Yes, thank you. Find the vector v which stretches between these two and then use the 1, 2, 3 as a fixed point and shoot the vector through it. So we have the vector v is going to be 5 minus 1 is 4, 4 minus 2 is 2, 0 minus 3 is negative 3. And we are using 1, 2, 3 fixed point because we did 5 minus 1 rather than 1 minus 5. And now I can do XYZ, which is a 3-dimensional line, Put down 4, 2, so 4t, no, sorry, put down 1, 2, 3, 1, 2, 3, and then plus 4t plus 2t minus 3t. That gives you your vector r of t, which is a vector 1 plus 4t, 2 plus 2t, 3 minus 3t. You are not done. This is equation of the line, but that line is infinite. I need t to be restricted between two numbers so that it travels exactly from one point to another point. Now, the first number is obvious, because if you use t equals 0, you're just having your first point 1, 2, 3. So that should be common sense. Now, how do you get 5 for x? T equals 1, thank you. T equals 1 will produce the second point. Plug in t equals 1 in each one of these, you get 5, you get 4, you get 0. Bueno? You need this. You have to have this because these are your a and b limits on your integral, your 0 and 1 limits. So it's not optional, right? Doesn't fall under the good. So now we know parametrization in 3. How about if I want to calculate down the helix? Yeah, right? What's a helix? It's going to be sine, cosine, and t maybe, or cosine, sine, t, or sine, t, cosine, depending which way it winds, right? Can we have a slinky? Sure, cosine, sine, sine, right? So it's not just a straight line. But luckily you know these from before, so we don't have to stress about that now, right? You had 2 lectures so far on parametrization, now we get to use it. So we are done with the line integral, what we call scalar line integral. The next part of this lecture is line integrals of vector fields. We covered vector fields yesterday. We talked about vector fields being functions that contain, so your vector field f was given as, so vector field f with the arrow, which can be magnetic field or electric field or gravitational field or Higgs field, whatever field you have. The wind and right, we said the flow of blood through the vessel, whatever, is f of xy if it's two-dimensional, and g of xy. So that's if it's two-dimensional. You plug in z and another one, function h, if it's in a 3D. So that was the vector field from last time. It's a function which assigns a unique vector to each point in space. So if I give you a point 1, 2, you will put 1 and 2 in f, 1 and 2 in g, and you will come up with the vector, I don't know, 7, -1. And then that's the vector, whether it's a force or whatever it is, associated to the particle which sits in that point in space. So now we also understood last class that a vector field covers the entire space. Vector field covers the entire space. So currently we are all in gravitational field of a planet, gravitational field of the sun, gravitational field of the moon, right? They all overlap, right? But we are also all in gravitational field of each other as well. We are also in electrical field and magnetic field of the planet, right? And all of those things. Now, we don't necessarily feel those because we evolved the way we did. Now, can we calculate line integral? Yes. Here is the definition. Let f be a vector field. Make sure you put the arrow. Because without arrow is antiderivative from Calc 1. So let f be a vector field that is continuous. On a region containing a smooth, oriented curve C, parametricized by arc length. Let t be the unit, so t hat be the unit tangent vector. Hey, hello unit tangent vector, welcome back to our lives. What was the formula for unit tangent vector? Yes, r prime divided by magnitude of r prime. Very good, very good. The tangent vector at each point of C consistent with orientation. I will explain every single word of this. It's just lengthy. The line integral of f over C is integral C f dot t ds. Guys, this is not what we are computing. We are going to have a theorem which will give us computational formula. What is all this mess? First we understand continuous, we understand vector field from last time. What is the smooth curve? Smooth curve is circle, is a straight line, is anything that doesn't have an edge or a corner. Can you integrate over a square? Yes, you can, but you actually have to do 4 independent line integrals because the square has 4 lines and it has 4 corners. So you actually have to break that problem into 4 separate integrals and do it. If you do the triangle, then it's 3 separate integrals. If you do a circle, it's 1 because it's smooth, it has no corners, right? So if you have x squared, perfect, it's smooth, no corners. Absolute value of x, no bueno. It has a spike, it has a corner, therefore you have to do 2 separate integrals, 2 separate line integrals to deal with each half of that graph for if you have absolute. So smooth curve means it has to, it cannot have, it's differentiable everywhere. It doesn't have any sharp edges, cusps, corners, anything like that. The next word is oriented. Well, you should remember from your Calculus 2 class at this point that all of your curves that you parametricize pick up, because they have extra parameter, they also pick up orientation. So that's the reason why you have cosine first for x and then sine for y in the equation of the circle, because you want to keep orientation and the movement to be counterclockwise. Now, if you put sine with x and cosine with y, then your orientation in that circle will be clockwise. So oriented simply means make sure you know which way the function goes. And it goes always in the way of increasing t. So the first t is at A, and then whatever the next value you computed, and the next one, and the next. It's just like connect the dots when you were 5 years old. Tangent vector, we already said that the formula for the unit tangent vector is going to be the r prime divided by the magnitude of r prime. Make sure it's a unit vector, that's why we have the hat. And then at each point of C, consistent with orientation, meaning that you can have t pointing inwards or pointing outwards, depending on which way the original orientation was. So for the circle, for instance, if you have the regular parametrization, which is the cosine for x and a sine for y, your vector t at pi over 2 would be pointing to the left, because the orientation is counterclockwise. Now, if you flip orientation and you have sine to be for x and cosine for y, then the orientation is clockwise, and then at pi over 2 on top, the tangent line would be, tangent vector t would be looking at the right side. So that's important because, you know, what good are you as an engineer? You design this amazing fan that is going to push so much air and then it spins the wrong way, so it does nothing, right? That's one of the things. So make sure, right, the orientation is consistent with the design. Then the line integral over C. So please recall that we were calculating the area of the curtain that was over the line C when we talked about regular scalar integrals. Now we have a vector field, and the vector field has a whole bunch of vectors. Guys, what I want you to think of is a fan. You have a fan, and the fan is on, and it's pushing air forward. At every point in space, right, every particle of air, every atom of air that is in front of the fan is being pushed forward. So you can pick any atom by picking the location, 371, and then you will have, because you have the function, right, the vector field, you have the function of that one being pushed forward. So now you have the vector field, and then you have the tangential component of that vector field to calculate how much stuff is above that line. So if my line is the unit circle, let's say the fan is 1 feet each way, so it's 2 feet in diameter, but it's 1 foot radius, so it's a unit fan, right? You have a unit fan, then you can calculate how much air is being pushed, but just in that, you have to imagine the tube, right? So where the tube would go on the circumference of the circle, right? Just that area, how much stuff is going, right? Not to be later confused with flux, which is going to be something similar but very different. So one more time, I don't even know if I can pull off to what I want to pull off, but this is your curtain, right? And your line C is this one, and it's wavy and blah, 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 which is why you have to parametricize. And when you have the parametricized line, each one individual is a function, and you can stick it in the integral, right? Now, what you're calculating there is the area of the rag, of the blue, right? So that's what you get as your scalar integral, which is the first part. Now, for the second part, what I'm having is a vector field. So now this rag is no longer a material, like a rag, like a curtain. This rag now, if I am able to make it into a tube like this rag represents the path where every single vector will take, right? If I have a fan on this end, right? Now this rag actually doesn't exist. Remember, the vectors are mathematical abstraction, right? That's what we said the first day. But why am I having a tube? I have a tube because I just want to show that if this one side is, you know, glued to the fan, right? The surface of this rag is, the vectors will be going alongside because you can feel the air hitting your face. So the line integral is compute how much volume of air, or how much area technically, or you have just along that infinitely thin, like eggshell tube. It's not calculating anything inside. That's going to be flux later on, all right? This one is calculating just the outer, how much air you get at the edge. Now, we do not parametricize over the arc length, and because we do not parametricize over the arc length, that's not the formula we use to compute stuff. We compute line integral by using the following formula. So, formula to compute this. So I'm not writing the title forever. Is going to be given by integral a to b of vector field f dotted with r prime of t dt. You see, I just want to stop talking here and not write anything else. Because if you really want to learn the most compact form for this, this is the only thing you learn. You know what the definition for f is. You know what the definition for r prime is. I don't care if it's 2D, if it's 3D. This is the multi-dimensional equation. It works for 2D, 3D, 4D, 17D. Because each one of these vectors can have 2 components, 3 components, or 17 components, depending on the space you're working in. So if you want the one formula that covers 2D, 3D, and 15D, that's the one. Now, the next thing I'm writing is immediately going to restrict you to work in a space, right? Because you are going to now have 2D or a 3D, depending on what you have. So now, if you have a 3D, then this whole mess is equal to integral a to b, and now you write out your f. Your vector field f is fgh, right? So it's f of x, y, z and then actually, yeah, and then each one of these is in terms of t. So I'm trying to see if we can't compress this. So eventually all of this works out to be in terms of t. So f of t, g of t, and h of t, that's your vector f. That was last class. Dotted by the x prime, y prime, z prime, dt. And you know that the dot product gets them all to add. So you have f of t times x prime of t plus g of t times y prime of t plus h of t times z prime of t, all of that in parentheses, dt. So if you are trying to memorize this equation, you immediately go insane, because it's just way too much mess. You memorize the vector equation up there, and you apply it to any space you want. The compact form with a C notation is f dx plus g dy plus h dz. It's not going to explode, right? All right, good.
I mean, it is a Windows, so. Just sounds like at least it hasn't yet.
So now we can talk about that problem 10 I wanted earlier. So problem 10, C is the unit circle. Oh, that's a 2D variant of this then. Nice. And your vector field F is given as 1x. So figure out the line vector. I'll be right back. You have the formula, you just need to plug in. You make sure you parameter size, obviously.
Yep. Dude, I'm trash on PC.
Because everyone on PC.
Yeah, I know. Dude, my teammates are gonna be gods. I'm gonna look so bad. Never mind. They're both trash. One's got 7 kills, the other's got 60. And the champion has 2,600. Oh, this guy I watched, Sword Kobe, has 15,000 kills.
Yeah, I started watching after you talked about it. He's insane. He gets like 20 kills a match.
Yeah.
Like at a minimum. Alright.
What? There's no way that's still live.
Yeah, I bet it's still.
Jerome Assetti is.
Jerome?
Jerome ASF. He's like a streamer or something.
No.
I don't know. You guys talk about video games.
Never
He like does YouTubes of video games.
I've never heard of him.
Yeah.
That's not right now.
That is.
No. It's
Oh, that.
He's still streaming.
Oh, he's in Minecraft.
I hope he watches it back. No, he doesn't. He definitely doesn't. Who has time for that? I don't even have time. Yeah. If one of you guys are in his Discord thing, you should like post the YouTube, like the timestamp thing to that. See if he watches it.
He has 5 million subscribers on YouTube.
Oh, no way. The wrong person.
He does. He does like Minecraft and stuff. And he's 25.
Oh, I thought you were talking about Nick. I thought you were talking about a professor.
No, this guy, Jerome, he does Minecraft. And he's like 25 and he's dating this girl who graduated from my high school last year. So she's 19, 18, and he's 25. And he's like famous, like they go on like vacations with like Minecraft. I can say for 17 months. But I know doing stuff much. Couldn't even tell you the name of this thing.
Someone's got to do this, otherwise he's going to do it.
I'm not doing it because I don't know.
Doing what?
I don't even know what that problem means.
C is the unit of the circle.
Is 1 to x? I don't
That's
know what that means though.
That's the vector field.
Yes,
So you just multiply that by R.
It's just dotted with R prime. The vector.
What's R?
The unit circle. So it's cosine x or cosine t sine t is R.
All set? Good. So, see, it's good you signed up for Calc3, right? Because if you never learn, how to joggle, now you did. to pick up all of your F's and G's and all right. So, unit circle. Immediately we know R is cosine t sine t. So that's what we have. Now those are your x and your y. Now for vector field, these puppies are f and g. The integral, I'll write it in blood, the integral is a to b of f dot what? Is anyone paying attention?
Yeah.
Huh?
And f dot R prime.
R prime, good. dt. So, for the two-dimensional version, we are 0 to 2 pi. I'll keep it a and b, still a formula. For two-dimensional version, my f is f times x prime plus g times y prime dt. All right, so what do I get? 0 to 2 pi for t. And then I have integral 0 to 2 pi now my f is 1 times the derivative of x, which is negative sine t, plus my g is x. But x is cosine t. Do we see that double substitution? Let me go one more time. I won't erase. So I have a gy. You see that my g is x, right? My g is x. But then x is cosine t. So that's why this is cosine t times y prime is another cosine t dt. Meditate on that double substitution if you missed it when you did it. You can't have x's and y's in this integral. It's dt, right? So you have to replace everything to be in terms of t. So you have to juggle multiple expressions at the same time. All right, so now integral 0 to 2 pi of negative sine t plus cosine squared, which is 1 plus cosine 2t over 2 dt, and that's problem 10. So now you can just integrate these expressions and be done. Integral of sine is negative. Cosine kills the negative, so it's just cosine t. Plus integral of 1/2 is 1/2 t. And the integral of cosine 2t is going to be sine 2t over 4, because there is a 2 that was already in the denominator, and then the over 2, that is because it was 2t. Everything computed from 0 to 2 pi. Now, this term dies because it's sines, and you have your cosine of 2 pi plus 1/2 times 2 pi minus cosine of 0 minus 0. Now, cosine of 2 pi is 1, so they actually cancel. 0 is gone, so the whole thing is pi. Make sense? So you will just learn to chase where all the variables are, right? One function plugs into another, and then eventually it all works out. As long as you remember that the only variable you're allowed to have when you start integrating is t. Not allowed to have x's, not allowed to have y's, not allowed to have fg, whatever. Just t everywhere. So plug in until you only have that. What is this good for? Well, calculating the work. Because if you're pushing the crate or a fridge or something, you do that along some kind of curve C, right? And since in Calc 1, the work is or in Calc 2, I think, work was the area under the curve. Now it's going to be area under the curtain, right? Because your path now is wavy. Maybe you had a few before you started pushing a fridge. So you exit Euclidean geometry and you push the fridge in a sine fashion. All right? It's the same integral, right? You have your force times the distance, right? What's the integral of velocity? What is the integral of velocity? Position. What's position times force? It's work, right? So it makes sense for this formula to be the work formula. So what do you compute to calculate work? Well, now why would you want to calculate this? Do you want to calculate how much work is done by power washer? Because that water under pressure coming out of the nozzle, that's a vector field, right? You have the speed at which it comes out. You can measure that. That's your R prime, right? Yeah. How about the destructiveness of the wind? That's like tornado, hurricane, right? That's going to be also something that it's a vector field because each particle of air is moving around. So you're going to have some kind of helix or some kind of circular motion or something. You want to have a vector field. And the vector field is going to have the strength, and then you're going to have the path which it takes, right? Casually through the neighborhood. So you want to calculate the work? It does. Well, work, it does. You know what I mean, right? It's a tornado. So destructive force of it. Mathematics of detonation. When they're designing new bombs. The shock wave. That's a vector field, right? It moves at a certain speed How much destructive power does it have? That's another one. Currents in the ocean. How fast are those moving? What is the force? Is it going to actually impact the cruise liner or not? Right? So calculating work is very important, and it's the same formula. Whether the work is done by a single force pushing or the vector field, which is a lot of force pushing, right? Remember, air pushes you. Air pushes you, and if the winds are strong enough, they can tip you over. I think 3 concepts left: circulation, flux, and I think there's something else. I have to take a look. They keep switching the content. Now we get to circulation. We all agree that fan spins and we feel the air hitting us. This is an air conditioning fan pushing the volume right now through these vents, right? So we want to know circulation and then later on flux. So let's take a look first at the circulation. We start with definition. Let F be a continuous vector field on a region D in R3. Oh, we have to be in the third-dimensional space now. And let C be a closed, smooth curve oriented in D also. And let C be a smooth oriented curve also in D. The circulation of vector field F on C is given by the line integral F dot T, and we know what T is, T hat, right? ds. Now you're going to go and say, how's this different than what we had in the previous formula? It's not. It's exactly the same formula. We're giving it now meaning. So, please say a few times to yourself word circulation. Circulation, 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 right? It implies movement and spinning, right? Does it? It does. So if it's measuring movement and a spin, does sun have circulation? Remember what it emits? It emits radiation in terms of rays. So sun is a radial vector field, right? Produces a radial vector field. What's the circulation for something like that? we should, use the common sense to answer this question. So you have a radial field. What do you think the circulation for radial field is? Look at the vectors. Are they spinning? No. 0. No spin. Anytime you have a radial field, right, it shines out. However, rotational field, F equals, what are we going to do? Negative yx. Let's do unit circle again. So rotational field, is it going to have it? Of course it's going to have it, because it's measuring rotation and motion at the same time. So I know that my R is cosine t sine t, and I know that R prime is negative sine t cosine t. I know this is my x, this is my y, this is my x prime, this is my y prime, this is my f, and this is my g. To calculate circulation, I just need 0 to 2 pi, and now I need to dot f with r prime dt. So 0 to 2 pi, f is given as, alright, so here we go. Vector field will have the component negative y, and y is cosine, so negative cosine y, and x is negative sine y, dotted with negative sine y, cosine y, which is our r prime. So this is our r prime, and this is our f dt. So what I have in the next line over here is do the dot. I missed something somewhere because I'm getting 0. I don't like it. Negative y. Oh, I used the wrong values, guys. See this? So I'm just going to redo this stuff, so I use the right values. It's crazy, but guys, I have f, which is, this is my f, and it's negative y, and this is my y, so that's negative sine t. And then x is the cosine t. And then g is cosine t. And the r prime is negative sine t. There we go. Holy nightmare. Good. So now, the dot product there, we have, we have negative sine t cosine t minus another negative sine t cosine t dt. Yeah, I switched it again. Mm-hmm. This is the part where we all should go home. Because I switched these. And you just, so sine squared t plus cosine squared t dt is equal to 2 pi, because you're integrating 1 and then you plug in 2 pi. Holy nightmare. So circulation is going to measure the rotation and the spin, right, of the vector field. Radial field, we saw the example. Radial field doesn't spin, and if you actually do this entire calculation for it, you guys are going to get 0 in calculations. So there's that. And it might be the last one, right? Oh, it is the last one. Okay, great. Guys, the only thing that is left is the flux. Now, this was one of the interview questions, actually, to compute the flux. No, not for my job. For ExxonMobil actually has the question to compute the flux when they were looking for new people to work in the alternative energy department. Oh yeah, be ready for the questions on the interview, because that's what the companies do now. They can be as picky as they want. I'll explain at some point. We have the whole spiel in a definition before the formula. So same intro, okay? Same intro. And then we finally have the flux is computed of F dot normal vector n ds, which is going to be calculated as A to B of f of t y prime of t minus g of t x prime of t dt. Now this calculates how much stuff you have across the area for the region that you are observing. The fan pushes all of the air in front of itself, right, forward. So the flux calculates everything that is normal to the perpendicular or orthogonal to the surface from which the vector field is, right, from the curve C. So everything perpendicular, so everything is poking out. Now, does this immediately screams that your radial field now is going to be maximum and the rotational field is going to be nothing? Completely opposite. Why is the radial field maximum? Well, guys, remember that when the sun shines out the radiation, right, gamma radiation and X radiation and the rest, that radiation emerges at a ray that came from the center of the sun. So at each point at the surface of the sun, the rays that come out are perpendicular to the surface, and radial field is actually what shines out, dotted with a normal vector on top of the curve that you are observing. So if you want to have a slice of sun, right, and see how much energy came out of that slice. So flux is perpendicular, and you can literally think of it as all of the air that is pushed from the fan. You see the blade spins in a plane, but all of the air that is coming out of it is perpendicular to that plane, right? So flux calculates how much stuff you have inside pushing out. Flux can also calculate how much stuff you have perpendicular to when you look the fan sideways, right, perpendicular across the ring. If you have a ball, think of a sun, it's going to radiate on all sides. You can calculate for the entire ball how much energy it pushes out. So there's a lot of stuff that you can do with these things. Calculation for this, exactly the same as everything else. Now, before you start panicking because you see the normal vector over there, well, we don't calculate normal vector or tangent vector or any other vectors because you have the right-hand side, which is the simplified version if you parametricize C. Right? Now, I'm not saying if you like pain, then by all means, go ahead right, and calculate in the left side. So you are going to get your vector field F as some F and G, and you are going to get your R as some X and Y. Then you will come up with R prime, which is X prime, Y prime, and those two puppies are in the formula. And you have your F, and you have your G, but you have to support those F and G with X and Y because you are not allowed to have X and Y stay. Right? It has to be in terms of T. So you have to replace all of those. Calculation is identical. So let's calculate, since now radial field is the one that it's going to be good for us to look at. Radial field, basic radial field is just XY. And that's the radial field which I drew earlier. It just shines out. Right? If you are on a unit circle, it just shines out all of these things. Again, C is the unit circle, and we know everything about the unit circle. So immediately you find your R, radius is 1, so just cosine T sine T, and you find the R prime because you need X prime and Y prime, so that's negative sine T cosine T. Let me see if I can do one of these problems, not to make a mistake. Parametrization is that T goes from 0 to 2 pi because we want the entire circle. If they want a half, they will say half. Oh, this is R prime over here. I gotta put the prime there. Okay, let's go. The flux equals 0 to 2 pi. My F, so these are my F and G. My F is X. My F is X, but X is cosine T. Cosine T times Y prime, it's another cosine T, minus G is Y and Y sine T, and then times X prime, which is negative sine T, and everything dt. So it shouldn't take long to see that this is just cosine squared t plus sine squared t, because you have negative sine times negative sine, dt, which is integral of 1 dt, which is 2 pi. Now, if you calculate the rotational field for flux, it's going to return a 0. Because rotational field spins. It doesn't shine out. It spins. So, right, when you rotate, you don't really cover space around you, right? You're just in that one spot. There's nothing going out. So circulation will work on rotations, and the flux works on shining out, right? Picking up how much stuff you have perpendicular to the surface that it's being radiated out. So that's our line integrals. We had a lot of concepts and a lot of formulas in one section. This is actually the longest section of Calc 3. This will be followed by the 2 short sections, and the course is over. So let's take a break and then go into the review.
Is circulation and flux